Up until now, we've concentrated on descriptive statistics, which are methods for organizing and summarizing data. And eventually, we're going to be moving into inferential statistics, where we need to draw conclusions about an entire population from just a sample. And because of this, we need to become familiar with uncertainty. And that's where probability theory comes in. The science of uncertainty is called probability theory, and it helps us to evaluate and control the likelihood that a statistical inference is correct. So, in this section, we're going to look at probability basics, and we're going to look at some of the rules of probability, and we're going to also talk about contingency tables and a few of the other rules that go along with probability. To define probability, it describes the likelihood of an event happening. And you'll see that I have event highlighted because we're going to talk about what that means more precisely as we move forward. In general, when outcomes are equally likely, a probability is nothing more than a percentage or a relative frequency. So that means that for an experiment with equally likely outcomes, probabilities are identical to their relative frequency or percentages. And we can say that the probability of an event is equal to the number of ways it can happen over the total number of outcomes. And this is called the probability for equally likely outcomes. And here is the formal definition. Suppose an experiment of n, and notice how it's capitalized here. That means its population has n possible outcomes, all equally likely. An event that it can occur in f ways, or frequency, has a probability of f over n of occurring. So that means that f is the number of ways an event can occur, and that is over the total number of possible outcomes, and that is equal to our probability. Let's look at an example. The top 5 officials are shown in the table below. Suppose we take a simple random sample of 2 officials of the 5. What is the probability we obtain the governor and the treasurer? First, we need to find all the possible samples of size 2. And so we will list out every possibility starting with the governor and moving down from there. So you can see that we have the governor and lieutenant governor, the governor and secretary of state, governor and attorney general, and the governor and the treasurer. Then you will start to list all of the possible samples starting with the lieutenant governor. You'll see that lieutenant governor goes straight to lieutenant governor and secretary of state, and it doesn't include the governor, and that's because it was already captured. So we're doing this without replacement. So there are 10 possible samples, and the probability that we obtain the governor and the treasurer, well, that only happens one time. So it is once out of 10, so the governor and the treasurer, 1 out of 10, or 10% is the probability. In this example, it's asking us to find the probability that the Attorney General is included in the sample. So we already have our samples listed here, and all we need to do is figure out how many times the Attorney General pops up, and that's A. So we've got 1, 2, 3, and 4. The Attorney General is included in 4 of the 10 possible samples of size 2, and that makes it 4 out of 10, or a 40% chance of the Attorney General being included in this. And this brings us back around to the essential equation that we have, the F over N rule, the probability for equally likely outcomes. So a probability of an event is F, the number of ways it can happen, over N, the total number of outcomes. But this only works if everything is equally likely. And before we continue, I just want to throw out some terminology to help with this section. We use the terms experiment and event, and you can use them in their basic intuitive sense. An experiment is an action whose outcome cannot be predicted with any sort of certainty. An event is one or more outcomes of an experiment. So by an event, we mean some specified result that may or may not occur when an experiment is performed. Let's look at an example. You want to see how many times a pair or a double come up when you throw 2 dice. So the sample space is all the possible outcomes. So if you throw two die, you might get one dice saying 1 and the other one saying 1. Or you might get one that says 1 and the other dice lands on a 2. And so on from there. And you can see that there is a lot of outcomes here. The event is the pair where both dice has the same number. So you can see that the event could equal 1 and 1, 2 and 2, 3 and 3, 4 and 4, 5 and 5, or 6 and 6. So that last example was just so that you could see the terminology for probability in action. But now let's do some more examples for the F over N rule. So the table gives a frequency of annual income of families. A family is selected at random, so this means that each family is equally likely. Determine the probability that the family selected has an annual income of between 50,000 and 74,999 inclusive. So what does that mean? Well, if we're going to throw out our F over N rule, it's the number of ways an event can occur over the total number of possible outcomes. And so let's check and see the frequency of being between 50,000 and 74,999. And you can see that the frequency is 15,754 over N, which is going to be our total number of possible outcomes. So that would be taking all the frequencies and totaling them together. And then we can take this number divided by this number, and for whatever reason, the division sign's not showing up. So just know that there should be a line in here. And if we do that, then what we get is 0.203, or you could say roughly about 20%. And with that last example, I hope that you realize that you could be asked for a bigger range where you might have to add a couple of different frequencies together. I mean, imagine that it had asked for incomes between 15,000 and say 50,000. Then you would have to take all of those and add them together and then divide it by your total. Here's another example. When two balanced dice are rolled, 36 equally likely outcomes are possible, and they're depicted in this picture here. Find the probability that the sum of the dice is equal to 11. So the dice can sum in two different ways, sum to 11 in two different ways, 6 plus 5 or 5 plus 6. So that means that our number of ways the event can occur is two different ways over the total number of possible outcomes, which is 36. And so the probability that the sum of the dice is 11 is roughly 5%. The meaning of probability. So probability is essentially a generalization of the concept of percentages. That is, when we select a member at random from a finite population, probability is nothing more than a percentage. And for interpretation, it can be quite easy. 0 meaning it won't happen, and 1 meaning that it will. What I'm showing here in this figure is two computer simulations of tossing a balanced coin 100 times. And this plays into the frequentist interpretation of probability, which basically construes the probability of an event to be the proportion of times it occurs in a large number of repetitions of the experiment. So when we're talking about probability, we can use the frequentist interpretation for understanding the meaning, but it's not really the definition of it. And of course, the equal likelihood model is not used all the time because there are assumptions behind it. Key fact 4.1, basic properties of probabilities. Property 1. The probability of an event is always between 0 and 1 inclusive. So it's not going to be higher than 1. It's never going to be less than 0. The probability of an event that cannot occur is 0. An event that cannot occur is called an impossible event. If it's 0, it's not happening. Property 3 is the probability of an event that must occur is 1. And that means that an event that must occur is called a certain event. Let's do another example. Thinking about the basic properties of probability on the last slide, find the probability that the sum of the dice is 1 and the sum of the dice is 12 or less. And when I say that, I am referring to two balanced dice that are rolled. So there are two die. The dice, you have two of them, can never sum to 1 because the lowest number you can get on each one is 1. So that would be 2. So the frequency of occurring is 0 out of 36. And that means that this is a probability of 0. It is impossible. Now, the sum of the dice is 12 or less. The dice will always sum to 12 or less. The highest number that we can get is 6 on both dice, and so it will always be 12 or less. So we're always going to have that. There's 36 ways it can happen over 36 possible options, and so the probability of this is 1 or 100%. And given what we've learned about probability, which of the following numbers could not possibly be a probability? A, which is 5 out of 6, B, which is 3.5, or C, which is 0. So what is the answer to this one? Well, go back to your rules of probability. It has to be between 0 and 1. 5 out of 6 is approximately 0.83. So that's between 0 and 1. 3.5 is not between 0 and 1, and obviously C is between 0 and 1. So which of the following numbers could not possibly be a probability? And the answer is 3.5. Here is some more practice for you to do. I listen to a lot of murder podcasts. If you ever need any recommendations, hit me up. And I'm not going to do this one with you. I'm going to give you the answers though, and I want you guys to try this on your own. So the age of murder victims between 20 and 59 years old is shown in the table. A murder case in which the person murdered was between 20 and 59 years old is selected at random. Find the probability that the murder victim was between 40 and 44 years old inclusive. So you just simply have to find out the frequency of this. And so 40 to 44 is just 900. Now, the next one is saying at least 25 years old. And that is saying that this person should be 25 years old or older. So that could be all of these numbers here together. And so you should add them together and you should get about 4,950. What about between 45 and 59 years old inclusive? So that's going from 45 to 59 inclusive. And your number here should be around 2027. And finally, under 30 and over 54. So now we're looking at these people here who are under 30 and the people who are over 54 years old. So then you'll be adding these ones together with this one, and you should get about 5,394. Before continuing, we need to discuss events in greater detail. And remember, this is a collection of outcomes. Recall that the sample space is the collection of all possible outcomes for an experiment, and the term sample space reflects the fact that in statistics, the collection of possible outcomes often consists of the possible samples of a given size. So when we have done things where it's like, oh, of a possible sample size of 2 or of 3 or of 4 or so on. An event is a collection of outcomes for the experiment, that is, any subset of the sample space. An event occurs if and only if the outcome of the experiment is a member of the event. Let's talk a bit about notation that you'll find in probability. So what you'll find is that many different events can be associated with a different experiment. And in this situation here, there are events that are associated with a card selection experiment. So consider these 4 events. We've got the event the card selected is the King of Hearts, the event that the card selected is just a king, the event the card selected is a heart, and the event the card selected is a face card. And when we use this notation, it's asking you to find out, for example, event A. So they want the event that the card selected is the King of Hearts of the single outcome, King of Hearts. And so for B, it's the event the card selected is a king. And so that is the event that the card selected is a king consisting of 4 outcomes: the King of Spades, the King of Hearts, the King of Clubs, and the King of Diamonds. And so this is just the way we say these things. So you'll get questions where it will say, what is the probability of A plus B, where A is the event the card selected is the King of Hearts, and B is the event the card selected is a king. Now, if you're kind of confused of what I'm saying, it's not like you have to do anything here. You just have to know that we're now going to use letters to then represent the different events that we could possibly have. And in probability, we use Venn diagrams. And did you know that Venn diagrams it's actually named after a person, John Venn, and he was a logician. So I guess that's like a logical magician. And so, anyways, he was developed the Venn diagram, and it's one of the best ways we have to portray events and relationships among these events visually. So when you look at this picture that I have here, what you'll see is that the sample space is the rectangle, and the event here is shown by the colored portion, or the colored disc, or you can use other geometric shapes as well. And we're going to go through a whole bunch of them because they will play into the rules of probability, and they help you with understanding how to solve. Letters are used to represent events like A, B, C, and D, and it helps us to display or write out all of our relationships. So you can see here that we've got A, B, and C, and all of these have different relationships among the events. So let's dive into those. So if you look at A, what we can see here is this is called not E, event not E. And this means that event not E consists of all the outcomes not in the event E. And we consider this to be the complement of E. And I'll explain that more mathematically, and it will help to make sense of it. And then we have the event both A and B occur. And with both events A and B, it consists of all the outcomes common to event A and event B. But then you'll see in C, we've got A or B, the event either A or B or both occur. And what this refers to is that event A or B consists of all the outcomes either in event A or in event B or for both of them. Now, because the event both A and B occur is the same as the event both B and A occur, event A and B is the same as event B plus A. And it's similar when we're talking about A or B, it's the same as saying B or A. To describe relationships among events, let's look at an example. And in this one here, we're going to think about playing cards. So for the experiment of randomly selecting one card from a deck of 52, let A equal the event the card selected is the King of Hearts, B is the event the card selected is a king, C is the event that the card selected, is a heart, and D is the event the card selected is a face. Determine the following event, not D. So they're asking us which is the event that a face card is not selected. So not D is the event D does not occur. The event that a face card is not selected. So we've got 40 cards in the deck that are not face cards. And so then the solution to this would be that there are 40. This one's a little bit more interesting. Determine the following event B and C. And again, we're talking about a playing card experiment where you're randomly selecting the cards from the deck of 52, and we're asking for the event B and C. It's the event both B and C occur, and the event that the card selected is both a king and a heart. So if you look down in here, we've got B is the event the card selected is a king, and the event the card selected is a heart. And so how many kings that are hearts is comprised or within a card deck of 52? And of course, there is only a single outcome. So consequently, B and C is the event that the card selected is the king of hearts, and it is a single outcome of there's only one. So events can be described as at least, which means it is X number, so any random number or more, at most, any number up to a certain number, and then inclusive. So it has to be at least a certain amount and at most another certain amount. And the best way I can give an example of this is if you've ever gone on to a real estate website and you're like looking up the different types of houses, you can put in parameters or filters in there. So some examples would be the event the housing unit selected has at most 4 rooms. And what that means that it has to have 4 rooms or fewer. So the next one is the event that the housing unit selected has at least 2 rooms, mean that it has to have at a minimum 2 rooms or more. And finally, the event that the housing unit has between 3 and 5 rooms inclusive. So maybe these people have, like 3 kids or something, and they're like, our minimum amount we can get away with is 3 rooms, but we would love to have 5 rooms, but we're not going to be opposed to anything kind of in between. So that means that at least 3 rooms, but at most 5 rooms, we don't want to pay for a 6th bedroom. So these are the ways that events can be described. This is one of the most important concepts in probability that will help you when you are solving problems in the future. We're going to talk about mutually exclusive events. 2 or more events are mutually exclusive events if no 2 of them have outcomes in common. And you can look at the Venn diagrams here that will show you the difference between 2 events that are mutually exclusive and 2 events that are not mutually exclusive. So if you look in A, we have 2 mutually exclusive events, and then in B, we have 2 non-mutually exclusive events. And this is going to make a big difference with the way you decide to make calculations. Now, when you think about something like mutually exclusive events, just ask yourself, do they have anything in common or not? If they have nothing in common, they're mutually exclusive. If they do have things in common, then they're not mutually exclusive. And I wanted to show you another figure. So in A, you can see you have 3 mutually exclusive events. And then in B, there are 3 non-mutually exclusive events. So in A, they've got nothing in common. In B, they have something in common. And in C, we've got 3 non-mutually exclusive events. So you can see that 2 of them have something in common, but one of them doesn't. So it becomes a non-mutually exclusive event. And we'll look at an example to finish this out. So playing cards for the experiment of randomly selecting one card from a deck of 52, let C equal the event the card selected is a heart, D is a face card, E is an ace, F is an 8, and G is a 10 or a jack. Now it's asking, which of the following collections of events are mutually exclusive? So C and D. Ask yourself, do C and D have anything in common? The event the card selected is a heart, and the event the card selected is a face. Can you have a face card that is a heart? So you can. So they're not mutually exclusive because they have a common outcome of hearts. Now C and E. The event the card selected is a heart, and the event the card selected is an ace. Do they have anything in common? Well, they do. They're not mutually exclusive because of the common outcome of ace of hearts. There is an ace of hearts. Now let's try D and E. D is the event the card selected is a face card, and E is the event the card selected is an ace. Can you have a face card that is also an ace? You can't. They're mutually exclusive because they have no common outcome.